This lab objective is to find out a black hole mass which is in the origin of the movement of an orbiting star. We can do that identifying the system, a star orbiting a black hole. We are going to use observations from the motion of the stars, which are x and y coordinates, took with the time interval of 1 Earth day. So we're going to find the black hole mass. We have the star mass. We have delta t, which is the time between each observation 1 Earth day, and our initial time is 0. In resume, with observational data plus the knowledge of the system properties, we can find out the total pushes and pulls of the system. So we open Python and we introduce the data we have on our problem, which is the star mass, which is delta t, the initial time, and we write the right physics. The program uses two coordinates: position in a time delta t, and in this way calculates the velocity of this change in position. With three position coordinates it's possible to find two velocities, and in this way the change in velocity delta v. The program interpolates all position data from the 2D motion, and from here we can know the velocity, the change in velocity, and multiplying delta b with the mass we can know the change in momentum delta p. So we run the program and we can see the movement of the star. This is the black hole, this is the star. We can see this blue vector is the net force, the yellow vector is the net force perpendicular, which is always aiming in the direction of the black hole, and we can see this black vector, and this is the net force parallel, which is responsible from the changes on velocity. The yellow vector always aims to the black hole, and this is the centripetal force. So in that case here we can see that there is no black vector, so there is a constant velocity in that moment, and here we can see that in some moment the system begins to accelerate because we see the black vector showing us the nature of the motion. Finally, the program gives us data about the motion. This is the time, this is the net force parallel, net force perpendicular, this is the position, and here we have the velocity. So with this data we are going to find the black hole mass. Introducing this data in our equation, so we put this data here and we find that the black hole mass is. What does it mean? How net force parallel and perpendicular are different from delta p over delta p? We know that when there is a small delta t, there is an approximation between the p dt and delta p over delta t. But this is only for small delta t, because when our time delta t is big, we have uncertainty about some data that we have. So in order to obtain this equivalence, we need to use a small delta t. But in that case, delta t is 1 Earth day, which is big, but compared with the size of the star path maybe seems not that small. However, there is a big uncertainty about the change in momentum when we measure that change in a big time interval. What if we change the black hole with different black hole in the same location and the result of this observation is still the same? I think that we have two different options. The first is if the new black hole have same mass, the observational motion is the same, which is the case of the problem. But if the new black hole have a different mass, observational motion will change. The new black hole have different mass, but if that's true, there must be a change in the motion of the star. But as we have the same values in the same time, that means that the mass is the same than the first black hole. The star could move in the same coordinates but in different times, but is not the case. So we assume that new black hole has the same mass than the other black hole. Thank you.